So hi, I'm Robert, and together with Hisham, we'll be giving a presentation on Intel XeSS. This is an AI-based supersampling solution for real-time rendering. Along with us, we'll have some partners joining. We'll have Rens from Art by Rens and Gabriel and Lucas from MagicWorks Studios, and they'll be showing how XeSS looks and how it was integrated into their titles. So before I go to talking about XeSS, I want to talk about the problems that it tries to solve. So developers are well aware that there are substantial problems when you try to render high-quality images with realistic shadows, lighting, and reflections, at the same time try to have a playable frame rate. And this has become even worse with high-resolution displays and new rendering techniques such as ray tracing, where you can see a clear correlation between the number of pixels you have to render and the performance. So if there's a way to reduce the strain on the pixel pipeline, that would allow to give substantial performance benefits. And that's the idea that came up when upscaling techniques have been devised. There's a number of techniques that are already available. And in principle, the idea there is that you want to render to as small as a buffer as possible and do all of the heavy lifting there. And then as a separate stage, try to upscale the image and reconstruct high resolution details from the few pixels in the input images. And since the upscaling phase will be relatively short, you have a net performance gain thanks to this operation. Of course, these techniques, the implementation of these techniques is not that straightforward, and they have their own problems. And they also not always provide the performance boost that you need. And this was a starting point for XeSS. And we set a couple goals ahead of ourselves to create a solution that also is a viable upscaler solution. So one of the most important goals is that we want to have a significant performance boost when you use XeSS. This is to make it worthwhile for the developers' time to integrate this technology into their engine. And if you we want a performance boost, you need to have a aggressive scaling ratio. So we should support scaling from, for example, 1080p to 4K. So that will be like a 2x scaling factor. And even with the scaling factor, we also have to preserve quality. So that's another goal that we have. And with preserving quality, we want to make sure that it works well across a wide range of titles. So this has to be a generic solution that doesn't require pre-title training. And so what is XeSS? So XeSS is a deep learning-based, temporally amortized supersampling technique. For those familiar with TA, it replaces TA in the rendering pipeline, and it has a very similar set of inputs and outputs. So conceptually, it's quite easy to make that jump from TA to XeSS. XeSS is a cross-platform solution. It works not only on Intel. On Intel, it has some benefits that Hisham will be talking about. It's also a generic solution that doesn't require pre-title training, so it would work out of the box for any title. The main concept is with XeSS that the rasterization and lighting stages happen to lower resolution buffers. And thanks to that, you have savings, right? You can render to a smaller buffer, you have less pixels to render, so the heavy lifting is done there on a reduced pixel size. After the rasterization phases, you have a set of G buffers. And in this case, I'm showing the depth, velocity, and the color buffer. All of them are low resolution. The color buffer is aliased. And all of these buffers are then passed to XeSS, where XeSS will upsample this image from, in this example, from 4K to 4K, from 1080p to 4K, and also apply anti-aliasing. So this is done as one pass. And thanks to that, you have a upscaled high-quality image, although you're rendering to a low-resolution input image. One important thing about XeSS is that it's a temporal solution. So it takes data from multiple frames to accumulate information that's not present in just one single frame. So even a case where you have a static camera, at the beginning of the rendering pipeline, you apply a jitter to the camera, to the projection matrix. And even for the static camera, this jitter will provide a different subpixel sampling location for each frame. So with each frame, we have information available that was not present in the previous frame. And all of this data is accumulated within XeSS. So it's stored internally. And then you need a velocity texture to be able to correlate how the data from the previous frames correlates to the current frame. So how each pixel location moved from compared to the previous frames. This data is then combined, and thanks to that, we were able to create the anti-aliased 4K image. I won't talk about what the depth buffer is used here for. I'll do it at a later stage of the presentation. But basically, at that point, you have the image reconstructed, and you're ready to send it to the remaining stages of the post-processing pipeline. And that's how XeSS works in a nutshell. And before I go into more details, I'd like to pass it to Rens, who was the first adapter of XeSS, and he created the Outpost demo that was used during XeSS's reveal during Architecture Day. And I'd like to pass it to him to get his opinion on XeSS.
Thank you, Robert. My name is Rens. I am a 3D artist and technical art director. Working with Intel, I had the opportunity to be the first adapter of their XeSS technology and use it during the development of the Outpost demo. The demo we built is a short playable experience that takes you from a frozen indoor environment to a snowy outdoor landscape. It shows how XeSS can help improve performance while at the same time preserve the quality of the original content. The demo is running on Intel Alchemist at 4K resolution and is built using Unreal Engine 4.26 with DX12. XeSS gives great performance increase for the base pass. This makes it possible to have much denser scenes, using objects with higher poly count to increase their detail. The Outpost demo uses 4K and 8K textures to create an equally detailed surface with scant resources. It was important to me that these details would be preserved, and thankfully XeSS maintains the original quality of these textures. To create these textures, I am relying on photogrammetry, using a series of 50 megapixel photographs to reconstruct the surface. The mood or atmosphere in the demo relies on volumetric fog, effects, and lighting, which are most often quite costly in terms of performance. To get the volumetric fog to look good, we needed higher settings that would normally be too heavy in native 4K. However, due to the fact that we are rendering to a smaller buffer that is later upscaled by XeSS, these settings would now become affordable. Performance benefits are also very noticeable in the translucency pass. The reduction here gave us the chance to use more effects without worrying too much about overdraw, which made the scene look more dynamic. Another area where XeSS works well can be seen in the lighting pass. While the demo uses baked lighting for global illumination, there is still a considerable amount of dynamic lights used. These lights at native 4K would take up a lot of performance. However, now with a reduced cost, we're able to use spotlights to create more visual depth and enhance the atmosphere of the demo. As part of the art style, the demo makes use of a lot of horizontal and vertical lines. These were created using pipes, railings, metal panels, and concrete surfaces, giving it an industrial feeling. These patterns are sensitive to anti-aliasing, but XeSS handles this well, since it's not only an upscaling solution, but the AI also performs anti-aliasing in the same pass. This removes artifacts such as pixelated lines and smoothing sharp edges. Compared to other AA techniques such as TAA, XeSS introduces less blurriness, so the final image is much more crisp. These are just a few high-level examples of how XeSS can help developers win back performance and push their content. I hope everyone is enjoying GDC, either in person or virtually as in my case. If you have the chance, I would encourage everyone to go see XeSS in action. And with that, back to you, Robert.
All right, thanks, Rens. One more thing I want to talk about, since upscaling right now is all the rage, there's a number of techniques. I would like to give a clear indication of different techniques that are available and what usages they are most suited for. So I'll start with spatial upscaling techniques. This family of techniques relies on just a single frame rendered at low resolution, and it basically upscales the image just from this one frame. It's usually invoked after the anti-aliasing pass. And the principle here is that it detects the well-defined features of the frame, such as edges, and tries to approximate the missing details from those features. The problem with this technique is that it works with a limited amount of information. It's just one frame that's low resolution. And to add to that, it's usually after the anti-aliasing pass, which further reduces the amount of detail. So you can imagine a situation where you have just a couple pixels on the screen, and just based on this one image, it's hard to say if this is a wire, a line, or just separate pixels. And that's why the quality of these techniques, spatial upscaling techniques, quickly degrades with the scaling factor. If you have an aggressive scaling factor, you will quickly see a decrease in the quality. The upside is that just because they just use one image, it's quite easy to integrate them into the engine. On the other hand, you have super sampling techniques, and XeSS belongs to this family of techniques, where they use consecutive frames. So not only one frame, but a series of frames, and they use the motion vector to correlate data between frames. In these techniques, usually anti-aliasing and upscaling is handled as a single problem, as one stage. And compared to spatial upscaling, they preserve quality much better as highly scaling factors. So there's this advantage. The problem is that they introduce their own problems, and even state-of-the-art supersampling techniques like TAU have problems like ghosting, blurring, flickering, or shimmering. And I'll actually talk about ghosting and talk how XeSS tries to and is able to alleviate this problem. So ghosting is an artifact that you see quite often with temporal anti-aliasing solutions, where if you have a dynamic object or the camera moves rapidly, you have these occlusions. So an object moves and pixels in the background are revealed that were not in the previous frames. And since these techniques rely on the history and tracking the history of a pixel, if you have a new pixel that was not in the previous frames, you have to know if you can use that history for the pixel or not. So you have to have a smart way to distinguish when you want to use the history and when you need to discard it. And usually we'll try to use the history as much as possible. And for these handcrafted algorithms, it's not always that easy to create an algorithm that knows when to discard and when to use a pixel from the history. And in result, you have this trailing ghosting artifact that you can see on the right side. And with XeSS, because it uses AI and neural networks are really good at detecting complex structures and images, and they are really good at recreating them. So we use this benefit to alleviate the effects of ghosting. And you can see it on the right-hand side that the image clearly doesn't have this ghosting artifact that's present in TAU. And for the same reasons, you'll see better quality if you look at blurring that TAU introduces. So in this case, if we zoom in one of the details of the scene, you can see the door. And if you look at the number is blurred and starts to fade in with the remaining elements of the background. With XeSS, it remains quite distinctive, just as all of the lines in the pipes. So again, the network here can distinguish these kind of details and structures much better than handcrafted algorithms and reconstruct it. So I'd like to sum up and just see where each technique can be used and what are the benefits of XeSS. So XeSS can achieve highest quality scaling factors without compromising quality. And this means that it can be used for next-gen titles where you have effects like ray tracing, micropolygons, and it's hard to achieve a playable frame rate if you run natively 4K. With the use of XeSS and an aggressive scaling factor, you can move the game from unplayable to playable, so across the 60 frames per second mark for these titles. With temporal, like traditional temporal supersampling solutions, you can also have a high scaling factor, but as I showed in the previous foils, you have artifacts that start to creep in. So the usability is limited. And then at the end, you have spatial upscaling. And because you just use one frame and you can't have an aggressive scaling factor, it means that the input image that goes to the upscaler has to be already at a relatively high resolution. So it means that the game already has to run at a relatively good or fast frame rate. So the usage, it will give a performance boost, but for titles that already have a reasonable frame rate. So you cannot use it like XeSS in situations where you're trying to move the game from unplayable to playable. So that's an important distinction. There are some limits to XeSS, of course. So one thing is that it has a fixed overhead that's dependent on the output resolution. And if you have a title, this overhead is not significant if you have a title that has a heavy pixel rasterizing a lighting stage. It's a fraction of the time that you spend in that stages. So for next gen titles, the overhead is small, and you will see a high scaling factor performance boost. With titles that have a light rasterization at lighting stage, the overhead might be significant, so the performance boost won't be that big. So that's another thing to remember, and when you think about upscaling solutions to use in your engine. And with that, I'd like to now pass it to Gabriel and Lucas from Mastercore Studios, that are one of the first adopters of XeSS, and they are creating their game Dolmen that uses this technique, and that's something that I want to show right now.
Thanks, Robert. Hello everyone, my name is Gabriel Neves Ferreira. I am CDO and lead programmer at Massive Work Studio. While talking, you'll be seeing in the background footage of the game Dolmen with and without Intel's latest technology, XeSS. Massive Work Studio is a company based in Brazil in a city called Natal, but we have been working remotely with team members scattered across the country. A little bit on the background of the game. Dolmen is a Souls-like game in which the player, which is a mercenary hired to retrieve Dolmen crystals from this planet, Revion Prime, finds itself in the middle of a planetary invasion. It is Massive's Work's first game and expected to launch later this year. In the past months, we have also been working closely with Intel in order to implement XeSS in Dolmen. Dolmen is built up using Unreal Engine 4, and along with Intel, we were able to smoothly implement this technology and integrate it with our current systems, in a way that we would benefit the most from its capabilities and providing the user a better and faster experience with next-gen graphics. This technology has helped us improve performance on already amazing scenes and reach 60 FPS with ray tracing enabled in places where we were already on our FPS budget. Now, to talk even further on the possibilities and benefits of XeSS and how it impacted us from a production point of view, Lucas Xavier, who is one of our best environment artists.
Thank you, Neves. Hello, my name is Lucas. I'm an environment artist from Dolmen. And when it comes to composing a scene, every piece of detail we can add, a rock, a small burst of particles from the ceiling, can help us create an immersive environment that makes the player feel connected and concerned of what is behind the next corner and behind the next door. I'm gonna let you see a little bit of what Dolmen is and looks. When composing a scene, we always need to take care of performance and the looks. We need to find the right balance between giving the players that feeling and also making them have a smooth experience. Here we can see a little bit of XeSS coming into play and comparing it to a native 4K. We have an improved experience with a higher performance without losing a single piece of quality and having sometimes even sharper looks and less ghosting. This is all thanks to the AI technology that super samples the image and provides us with amazing looks at a cheaper rendering cost. Intel XeSS technology has enabled us to reach 60 FPS with ray tracing, which without an AI super sampling technology it just wouldn't be possible. In a sci-fi game with a unique Lovecraftian vibe, and the fast-paced scenes and the combat required us to push the technology to its limits. This environment had a lot of small details and expensive elements that created the immersion for this cave, giving it a unique look. XeSS and Intel helped us work with our minds at ease for the performance, and we could push and create this amazing game for you. Thanks, and back to you, Robert.
All right, thanks, Gabriel and Lucas. I'd like to talk about how to integrate XeSS into the engine. So first of all, there will be an SDK that can be used to integrate it into any gaming engine. And this SDK will support all GPU vendors. So for the Intel path, for the Alchemist platform and future Intel platforms, we have XMX acceleration that allows to speed up AI inferencing operations, and Hisham will talk about that. So for Intel, we'll have a special path, but for all platforms that support DX12 shader model 6.4, the XeSS will also work, and it will basically use HLO cell shaders for the implementation. There's one intrinsic that's needed. That's the DP4A intrinsic, and most modern GPUs support that. So XeSS will work on most GPU vendors. Another important fact is that the SDK will be open sourced. And from the game developer's perspective, there'll be just one interface, right? Regardless whether it's Intel or any other vendor, there'll be one interface that they have to interact with, and all the platform detection and dispatching will be handled internally. Hisham will talk more about it, so I'll just skip it and go to integrating it into the engine. One more baby thing before that is that both Rens and Massive Works Studio use Unreal Engine for their development. And for Unreal Engine developers, there is a plugin available that significantly simplifies integration of XeSS. It's basically a copy-paste operation and then just enabling XeSS from the editor. And with that, you're able to use XeSS seamlessly in your game. This works for UE 426 Plus and Unreal Engine 5. For earlier versions, like Unreal Engine 425, you need a code patch to apply this. So how to integrate XeSS into your engine? If you already have TA enabled, it's quite a simple substitution. Basically, it's inputted in the same style in rendering pipeline. It's just after rasterization and lighting, and before all of the remaining post-processing stages, like artistic effects or tone mapping, all of these stages. But if you don't have TA enabled in your engine, it's still just a couple of steps that are needed to integrate XeSS into the rendering pipeline. First of all, XeSS takes a couple of inputs that are required each frame that has to be passed to it. So the first one is the jitter offset, and ideally this should be a Halton sequence with a length of 32 samples. Then you have the color input, and this can be an SDR, HDR linear texture with a linear color input. If you do not have exposure already integrated into the color buffer, you have to pass an exposure texture or a CPU constant that allows to compensate for the camera exposure. Then another parameter that you need to pass is the dilated high resolution motion vector. So actually you have two options here. Either you can pass the high resolution motion vector, or you can pass the low resolution motion vector, and along with it pass the depth buffer. And having these two information, XeSS internally can upscale the motion vector and do the dilution itself. So to simplify integration, you can just pass the low resolution motion vector. And the last parameter you need to pass are some resolution controls. And that's because XeSS supports dynamic resolution scaling. So for each frame, you can have different input resolution, and these controls allow you to specify it. As an output, there's a simple output, just one texture that's in the target resolution side, and this is a texture you can pass directly to the remaining stages of the rendering pipeline. And all of the history is maintained internally, so that's not something that the engine has to worry about. So going a bit more into details, to integrate XeSS into the engine, first of all, you should take care of jitter. So ideally, you should have a static scene with no camera motion, and just make sure the jitter is passed correctly. So XeSS requires a subpixel jitter offset, and it has to be applied for every frame. As I mentioned, ideally, it should be a Halton sequence, and the range of the jitter should be within minus 0.5 to 0.5. And this jitter can be applied directly as a shear transformation to the camera projection matrix, and you can use this equation to apply it. And once you see that with this jitter applied with the static camera, the output from XeSS is stable. There's no shaking. You have no artifacts. This is a stage where you can go to the next step, and that's applying a bitmap bias. So if you're rendering in a lower resolution, a low resolution bitmap will be selected. And you want to preserve as much detail as possible with XeSS. So you can apply a bitmap bias to make sure that a higher quality setting of the texture is selected for all textures that are used. And here you can use this formula again to calculate what is the bias that you want to use. It's log2 of input width by target width. And we have this additional parameter here that can be used for tweaking. So maybe I'll just start with an example that for 2x scaling, this formula will give you -1. So that's the bias you have to apply to textures. And additionally, you can use this -x parameter to tweak it a bit. So we recommend starting with 0, so like with the default setting. But then you can increase it if you want to increase the quality of the textures. Like, for example, Unreal Engine uses 0.3 for TA, and that's what we also use for XeSS. With a bigger bitmap bias, there is a risk of introducing flickering corruptions and decreasing the temporal stability. So as I mentioned, start with 0 and then experiment if you want to go with a higher bitmap bias. And then once you have that, the last stage, and this is the final stage, is to make sure that the motion vectors are correctly. So the motion vectors here specify the screen space motion in pixels from the current frame to the previous frame. So basically tell you how the location of a pixel changed compared to the previous frame. That's in screen space. And the velocity combines two factors. One is the dynamic objects, the movement of dynamic objects, and the movement of camera. So having these two factors, you can flatten the velocity to have a single information about the pixel's motion. And as the SDK allows you to specify this either as a low resolution undilated motion vector, and then you have to specify the depth buffer and give it to XeSS. So XeSS can internally upscale and dilate this motion vector. But if you have a high-res motion vector, you then must dilate it yourself. And the simplest approach to dilating the motion vector is to take the frontmost pixel from a small neighborhood. That's why you need the depth buffer. And once you have that frontmost pixel from the neighborhood, you take the velocity of that pixel for a small region, like 3 by 3 square. And thanks to that, the velocity will be diluted. And you can see on these images, like the gaps in the figure are filled out because they're diluted. And you won't be introducing aliasing artifacts related to velocity. And that's it, basically, from the integration of XeSS. And I'll now pass it to Hisham for more details on the underlying technology, that if you run it on Intel, and some more details on the SDK itself. So passing to you, Hisham.
Thanks, Robert. So now we'll go into a little deeper into the technology itself and how we are using XeSS to accelerate on Intel devices. So agenda for this section will be, we'll continue from what Robert talked about, the high-level overview. Then we'll briefly talk about the runtime flow of XeSS via DX12 and Intel software stack. Then we'll give some brief breakdown on the software and hardware stack behind XeSS, the building blocks for it, and briefly touch on the Intel AI Accelerator that we are using to accelerate XeSS through Intel hardware architectures, especially Intel Arc devices. So the technology behind XeSS, right? As Robert touched on it briefly, the idea is it's a super sampling technique which reconstructs a low resolution frame to a high resolution frame, running at a fraction of cost compared to running at full resolution. Example 4K, right? So idea is you reduce the resolution and you use this technique to up-res the frame to a high resolution, and which gives you a lot better performance without compromising any quality. So the technique we are using for XeSS, it's machine learning based. We have optimized neural network that specifically designed for XeSS, which has a lot of operator fusing that's not available through standard AI frameworks. So we use that to accelerate XeSS faster on various devices. And this neural network heavily uses Intel AI Accelerator that will be introduced through Intel Arc GPU family. So the accelerator is called XMX, Intel Matrix Multiply Extension, and it uses heavily that technology to get the performance it needs from the underlying hardware. And this is DX12 based. We use Intel vector shading language, which is very low level vector shading language, mapping directly to Intel vector hardware architecture, giving the most efficient performance for XeSS. As mentioned earlier, you can see here the top bar shows you what kind of performance you'll get if you were rendering at full 4K resolution. And with XeSS, you can reduce the native resolution down and run XeSS as a post process, and upres the image to the same as the native 4K resolution in this case, with a fraction of a cost. As you can see, your time it takes to render or get the full frame is much lower compared to as if you were doing native rendering. And here I'm showing two kind of hardware that is used here. XMX I talked about, which is the middle bar, and then the devices that doesn't have XMX and the devices that have DP4A capability, we will internally transparently map those to DP4A based instructions. So a little bit on the runtime flow, right? So I think Robert showed it also briefly on this. So XeSS runs right after the rendering phase, and it will run the neural network, generate the upres frame, and then you do your rest of the post processing before displaying out. And little bit deeper dive, how does it look like on Intel stack, right? So these are the main blocks that accelerating XeSS. So you start from game, which interface with your SDK API. Here I'm showing it Intel XeSS API. This is the SDK API, which will talk to Intel XeSS implementation, which will talk to our cross compiler block, which is responsible for taking the vector shading language I talked about earlier, and make it compile for DX12 driver and runtime, and then it communicates with the driver to send the work to any of these GPU. And depending on which GPU you use underneath, it will either use XMX, as I mentioned earlier, or use DP4A. And one thing note, I'm showing here two boxes, which is Intel XeSS, right? So the reason being, I think we will always ship our latest Intel XeSS with the graphics driver, but then there will be an option also for games to integrate the version they tested with the game, right? So if that happens, that version will take precedence over the latest graphics driver version. So that's why I'm showing you here two versions. So initial few implementations, they probably will be almost same thing. Little more on the runtime flow. As I mentioning, there will be two main phases of XeSS. One is initialization phase. That's where you build up the neural network, you upload the weights, you create all the resources wherever necessary and keep it handy, right? And during execute phase, that's supposed to run per frame, where low resolution frame will be given to XeSS. XeSS will encode the XeSS layer library will encode the XeSS commands, which is the neural network, to run on that frame, and output from this will be high resolution frame. So the flow is like this. As I mentioned, you do init, then you execute. In this case, execute doesn't mean it's running on GPU. Execute means it's recording the commands into DX12 command buffer. So green here is the application portion, blue here is XeSS portion. The application can decide to record their own commands, including rendering commands here. Then XeSS gets run, use the same command list, command buffer to put the XeSS command in there. After that, game can do other commands into that command buffer, and then eventually you submit to the GPU. So as you notice, there's no back and forth between CPU and GPU here. You can decide to encode everything on the CPU timeline and submit to GPU and make CPU do other work after that. Okay. Moving on. So I mentioned about XMX. So this is a newest technology that we are introducing with Intel Arc GPU family. So this is how it looks like on the hardware point of view at high level, right? So you will have all these EU arrays, which are the main core of running the neural network and any compute operation. And inside that EU array, you have this is the block, right? So you have FPU unit, integer unit, and then XMX unit. And depending on the hardware, you might or might not have the XMX unit. As I mentioned earlier, XMX is getting introduced with ARC, and before XMX devices, you'll have hardware that will have DP4A unit, which will appear here. And DP4A, the folks that are not aware of this, it is basically dot product for accumulate. So it does 4 dot products and accumulates it, and we pack int8 values into 132-bit registers and perform dot product and accumulate into 32-bit value. And XMX is actually, we are doing pipeline of dot products, which is 4 pipeline of dot products and accumulating into 32-bit values. How does it run on Intel Arc devices, right? So say game application running it on Intel Arc devices, it will call the Intel XeSS API, and Intel XeSS API will detect what kind of device is underneath from the DX12 device. It will figure that info out, and from that it will basically pick the implementation which uses XMX, and we will have neural network implementation based on XMX, based on DP4, as I mentioned earlier. So depending on the device, it will pick the XMX implementation, use the Intel vector shading language, compile it for DX12, run it on Intel Arc devices which has XMX. Also, if you are on non-Intel XMX devices, for example XC Iris Plus or XC Max devices, it will detect those capabilities. The Intel XeSS layer, this will detect these capabilities and determine which network implementation to submit to the hardware. So as I mentioned earlier, for those devices, it will use the DP4A implementation to run it on those devices. So in short, we intend to support all Intel GPUs starting from Tiger Lake that has DP4A plus support. So that's our intention to do it and go from there. All right, so this is the performance upside you'll see with XeSS as shown earlier. So Rens created a demo with XeSS. They enable XeSS in their demo itself, and this is the performance upside we collected in our labs. And here you can see I'm showing 2 sets of numbers. One is at 4K target resolution, other is at 2K target resolution at various quality settings, right, or various scaling factors. So what those scaling factors are this, right? So this is currently how it stands, but this is subject to change, but this is where it stands right now. So at ultra performance, you are scaling down by 2.3 before doing the rendering, and XeSS is responsible for taking it from that resolution and converting it to the native resolution you're targeting. So for example, performance is at 2.0 scaling, meaning you target resolution is at 4K, you take it down by 2x, both x and y direction. You give it to rendering, render will render at that lower resolution. XeSS then come into picture. XeSS will upraise that frame from that lower resolution to the higher resolution you're targeting, in this case 4K, and go from there. So this is the performance upside you can see for the whole demo itself for those frames, right? Doing XeSS, and you can see anywhere you can go from 2.5x to 20% benefit, depending on the quality level, depending on how much reduction you're doing on the input resolution. Okay, so that's the performance upside. So that's pretty much it. Thanks for watching, and let us know if you have any feedback, comments, suggestions on this, and let's go from there. And will be exciting to see this technology in all your games and so on.